All right, welcome back. So let's look at this example right here. A card with an initial horizontal velocity of negative 20.5 meter per second experiences a sudden deceleration until coming to rest in 6.8 seconds. Well, just reading this, right, we can see that this is pretty much a one-dimensional kinematics. And doing a rough sketch, you can see that taking this to be the car, it is moving to the left. That's why we're given velocity as negative. So that means velocity here is negative 20.5 meter per second. Remember, x hat means that it's a horizontal velocity. So this will be then our initial velocity. And then let's call this, point A. What happens? We don't care what happens before point A. What we know here at point A, it starts slowing down. It slows down until it reaches point B and stops. So V final here is 0. And what we're given is the time. The time going from A to B will be then 6.8 seconds. All right, so that means more or less we can still write down a table of what was given. Initial velocity 25, sorry, negative 20.5 meter per second. Final velocity 0, and the time is 6.8 seconds. All right, so what we want to find for part A will be then acceleration. What is acceleration? Now, what we have here is, this is a non-uniform motion. Which means object is changing its motion. And it's only along the horizontal axis, so it's a one-dimensional non-uniform motion. All right, so we can assume that acceleration is going to be constant. And the idea is if you have a constant acceleration, non-uniform motion in one dimension, so you have those 4 kinematic equations. Let's write down again. So equation 1, final velocity equals initial velocity plus acceleration times time. Equation 2, x final equals x initial plus initial velocity times time plus 1/2 acceleration times time squared. Equation 3, final velocity square equals initial velocity square plus 2 times acceleration times displacement. And finally, fourth equation, delta x equals initial velocity plus final velocity divided by 2 and times time, the whole thing. All right, so what you need to do is just look at what you're given, and based on information given to you and equation that we can, work with, see which one works the best. Sometimes you might have more than one equation giving you the right answer. And what you want to do here is just find the one that basically can give you the answer the simplest way. Okay. So here we have initial final velocities, we have time, looking for acceleration, and you can see that equation 1 does exactly that. So for equation 1, using that, we can say, okay, for part A, final velocity equals initial velocity plus AT. So we can rearrange things, right? Remember, this is 0. So then initial velocity plus AT. Then we can say then AT is equals to negative initial velocity. So kind of like rearrange it like that. And then divide both sides by time. So acceleration equals negative initial velocity over time. So here it was negative 20.5 meter per second for velocity, divided by time of 6.8 seconds. Negative, negative cancel out. So we get 20.5 divided by 6.8. We get 3.01 seconds. There you go. So that means, meters per second square. This is the acceleration. There you go. So 3.01 meter per second square. All right, so this will be then part A. Part B, it says, what is the car's displacement during the first 5 seconds of the motion? And what will be the velocity at that 5 seconds? So this will be part B, this will be part C. Okay, so let's look at what we have. So we want to find displacement and velocity final, but when time is equals to 5 seconds. But here's the thing, right? So acceleration is for the any given time, and it's constant. That means we have now acceleration, and we know that it will never change. So for part B, we still can use the initial velocity. We can use acceleration, and now we're given time, which is 5 seconds, and we can then solve for the displacement at this point by using equation 2, which is final velocity independent, because we don't know how fast it's moving at 5 seconds. We know at 6.8 seconds it stops, but at 5 seconds it's still in motion. But again, we're fine because equation 2 allows us to solve displacement for the displacement without requiring final velocity. So x final equals x initial plus initial velocity times time plus 1/2 at squared. Initial position is 0. Initial velocity negative 20.5 meter per second times 5 seconds. Then plus 1/2, then times acceleration, which is 3.01 meter per second square times 5 seconds square. So x final will be, calculating this first term. So we got negative 102.5 meters. You can write seconds cancel out and you have meters. Then plus, then calculating the second term. There is 7.6 meters. All right, so we calculate this. So we get 64.9 meters. So negative, so that means, if the car was at point A, which is, let's say, taking the origin, then it will be negative 64.9 meters relative to that in the left direction. This means that moving to the left. So it will move to this position at the time of t equals 5 seconds. Then, can still continue moving a little bit until it fully stops. This will be then, again, displacement at t equals 5 seconds. Now, let's calculate what will be the speed for part C. Well, again, this will be easy because we can say final velocity equals initial velocity plus a times t. In this case, we're using, again, negative 20.5 meter per second, then plus, then 3.01 times 5 seconds. Now we can calculate this. You can see that it's negative 5.45 meters per second. That means it decreased by a factor of nearly 4, right? From 20.5 meter per second to the left to 5.45 meter per second to the left. And it is still, moving at that point, at 5 second, time. But obviously, just a few seconds later to then it will come down and stop. All right, so then this will be then part A, the acceleration, part B, the displacement 5 seconds, and part C, which is the final velocity at 5 seconds.